Hello, so today is Wednesday, November 18th, and this is model-based imaging, and we're going to pick up on, do some more markup chain stuff. Okay, so I'm going to talk about reversible markup chains, and I'm going to review the full balance and detailed balance equations, and then I'm going to go back to hidden Markov models and Markov chains. So I kind of did the theory here first, and then I'm doing the application. And then we'll come back to the theory, because we're going to do stochastic sampling, which uses ergodic Markov chains, okay? So last time we talked about how you can establish that our Markov chain is ergodic, right? So the basic equation is that basically pi of n plus 1 is equal to pi of n times p, right? So this is the probability distribution at time n, and this is the probability distribution times n plus 1, and that's the transition probability, which is a matrix, and that matrix is square, okay? So the hope is that the limit as n goes to infinity of p to the n, right? That's equal to pi infinity through pi infinity. It's basically all the rows of that matrix are the same. The hope is that. Then we say the MC is ergodic. Okay? So then we can ask the question, well, we can say, well, how do we know, how can we prove that it's ergodic, okay? On what conditions ensure that it's ergodic, okay? I talked about those last time, but let me just sort of talk about some other related ideas, okay? You know, it's not always, I mean, when you write a proof mathematically, you go A implies B, implies C, implies D, implies E. You know, you go on a linear chain, and that's fine. And that's easy to analyze, but it's not always easy to understand. Actually, humans are extraordinarily bad at applying logic. It's very unnatural for humans. So I don't necessarily go in a linear order. I kind of get ahead, and then I come back and fill in. Often that's an easier way to explain something. When you're trying to write technical writing, it's often easier to start off by giving the conclusion and then starting filling in the details as why the conclusion is true, which is like what you do with a proof, right? You state the theorem, and then you give the proof, right? But, you know, because you could say, well, you just go in a line, but if you just go in a line, it would be incredibly unclear to people what you were talking about, because you'd be like just saying weird little things like you'd set this equal to that, and people would have no idea where you were going, right? So in that vein of trying to understand where we're going, okay, if this is going to happen, right, then what we'd expect is that if we have pi infinity, that's the stationary distribution of the Markov chain. If the Markov chain achieves the stationary distribution, or if we started it off in the stationary distribution, and we apply the transition P, what's the result going to be? It's going to be the same thing again, right? Because that's the whole idea of what the stationary distribution was, right? Okay. So we'd like to so the question is so what we'll put is so we expect the Okay, now, if this is a stationary distribution, this should hold, right? But I would actually go further and say, if this holds, it's got to be the stationary distribution, or it's got to be a stationary distribution. Okay, so a Markup chain can be could be non-ergodic. Okay, it may be that the Markup chain isn't ergodic, at least the way I'm defining ergodicity, but it does have stationary distributions because it could have multiple stationary distributions. It could be here. It's got to be unique. Okay, so independent of where you start, it's got to be the same distribution, but it might be non-unique. So example would be, let's say we have like a Markup chain with 10 states, and we have another Markup chain with 20 states, and we just take the two Markup chains and we just merge them together. Okay, so now we just concatenate the states, and now we have 30 states. We have the same transition probabilities. You can't go between states. So once you can start in the first 10, you can't go to the second set. If you start in the second set of states, you can't go back to the first. So you're going to have an then the Markup chain is going to have two stationary distributions, at least two. Actually, it has an infinite number of stationary distributions, because if you started off in the first set of states, you'll always stay there and reach some stationary, but you'll still have a different stationary distribution for the second set. So my point is that it doesn't have to be unique, okay? Okay, so, but if this holds, then it has to be a stationary distribution, right? It's got to be a stationary distribution. So we expect that pi is the unique solution to pi times p equals pi. So if there's a solution to this, it's got to be a stationary distribution, right? And if there's a stationary distribution, it has to be a solution to this. So it's really an if and only if condition. So these things here, this is called the full balance equations. Okay, those are the full balance equations. Why are they called the full balance equations? Well, I don't know, because there's a perfect balance between the distributions. I mean, when you think about it, it's like if you drew all the states on one side and on the other, and then you have this transformation, and the output is the same as the input, so it works, okay? I don't know. Maybe that, okay, so this is the full balance equations, okay? Now, conditions, okay, conditions for ergodicity. And let's face it, ergodicity is a really interesting, it's a kind of a cool word, right? I mean, because if you said it at a cocktail party, people would be like, what does that mean? And you say, you don't know what that means? So you can kind of impress your friends with it, I think. You go, well, they understand ergodicity. Okay, oh shoot, I thought I had this on. Did it go off? It's going to take me a little while to log in. Okay. Okay, so there's a few things we have to do while I'm waiting for that to boot up. One is states communicate. Okay, so I'm just, for this I'm going to say the first condition is Oh, I gotta clean this silly nonsense up. Oh. Okay, so I'll just go through. Oh, not blank, laptop. There we go. Hopefully that you can read that on that screen there. Maybe. I tried to point it up so that it would get, the AGC would be happy.
There's words on it, I just can't read it.
Oh, okay, but there, and if for the people in TV land, they can always go to the notes. If it's hard, it's not as legible. So we have to have a concept of communicating states. So two states, I and j, communicate if with there exists an n and an m, such that pij n is greater than 0. So what that means is that in n steps, it is possible to get from state I to j. N may not be 1, but there's got to be some n that will get you there, okay? So, and some m such that, not necessarily the same value, by the way, such that you can get back from j to I, so they communicate. Okay, yeah?
Is it equivalent as saying that if you start from I, in n steps, there is a non-zero probability to reach to j?
Yes, that's exactly. That's what you just said in words is what that is mathematically. It's identical, okay? So, all right, is that clear? Does it make sense? Because Pn is, so maybe this notation is, I could have put brackets about it, okay? Because it's, what you're saying is you're raising p to the power n, and then you're taking the ijth element of that matrix. So that's exactly the probability of getting from state I to j in n steps, okay? And it has to be greater than 0. Because if it's 0, then you can't get between the states, right? And then this is the probability of getting back again. So basically, it's saying that there's a non-zero probability that in n plus m steps, you can make a round trip. You can get to the state and come back. Okay? So if that happens, then we say I and j communicate. It turns out that it's easy to show that communication is a it's a property that what do you call the property? That is it's an equivalence. Okay, it's an equivalence. So I think that's the technical term. It has the property that if I communicates with j, then j communicates with I. Okay, so then it turns out that anything that has that property, of that commutative property, it's called an equivalence, then it's easy to show that it must partition the set of states, okay, into sets that communicate. So in other words, if you have a set here and a set here, if every two states here communicate, right, and if every two states here communicate, then if this state communicates with that, right, then they all communicate together, okay? So the idea is this, that whenever you have a property like this, you can separate this, you can partition. The word partition has a precise meaning, okay? Partition means that you can take all the states and separate them into groups that are disjoint, and their union includes all the states, okay? I think partition has a familiar semantic meaning, and that's what it means, okay? So the point is that it partitions the states. So if you partition the states into communicating subsets. If there's only one subset, then you say that it's irreducible. If there's more than one subset, then it's reducible. So a discrete a time state homogeneous Markup chain is said to be irreducible if all I and j communicate, okay? So in other words, it's always possible to get from any state to any other one, right?
Of course.
Yeah.
How non-zero do the probabilities have to be?
Well, yeah, non-zero means not zero.
I meant like you can make something effectively so small it's effectively zero.
Right, but here we're living in math. I knew your question, by the way, and it's a good question. I didn't mean to make fun of it, okay? But my answer was intentionally non-responsive, okay? Because here we're living in math land, okay? So not zero means not zero. So as you observe, that means it could be like equal to 10 to the googolplex squared, right? It could be the factorial of 10 to the googolplex squared over 1 over the factorial of 10 to the googolplex squared, right? And that would still be just perfectly fine. It would meet the conditions of the theorem, okay? But in some sense, it wouldn't be satisfying from an engineering perspective, okay? By the way, here's an interesting thought. The factorial of 1 to the 10 to the googolplex squared, okay, is a small number compared to most other numbers in the real line. Should I say that again, or maybe that's obvious to everyone? I mean, it's like the old thing that they, you know, when you're talking to little kids and they go, well, what's infinity? Okay, well, why is the real line infinite? And you go, well, pick any number, and then pick a number. And I said, well, take that number plus 1, right, and it's larger. So there is no largest number in the real line, right? So no matter how big you make it, you can always take any number, multiply it by a googolplex, and it's a lot bigger. That's something you really have to keep in mind as a signal processor, because the real line is really, really, really big, okay? So you can fit an awful lot of stuff in there. So if somebody says, pick a number, the probability of you getting the right answer, even if you say it's an integer, okay, is 0, okay? Now, as a practical matter, it's not 0. You know, well, we won't go into it, but it should be 0, right? Because there's a lot of numbers on the real line. So a discrete time. Oh, okay, so we did this. That's irreducible. Okay. The periodic. Oh, periodic will make your head hurt. Okay, I'll just read it. So it seems like it should be very easy to define periodic, and it's not. It's sort of tricky. So we denote the period of a state, I, by the value di, where di is the largest integer, so that Pn of ii equals 0 whenever n, boy, this is getting long, is not divisible by d. So what it says is that, okay, let's forget about the largest integer part, okay? The largest integer you have to have there because 1 will always work, okay? Because, okay, Pii is, every value is,
From one state.
is not divisible. I have to be a little careful about how I define divisible. Is 0 divisible by 10? I think 0 is not divisible by 10, okay? So So every number is divisible, every positive integer is divisible by, do I see here? I should, actually, you know what I should have put in here for n greater than 0, okay? I should have put here n greater than 0. Actually, someone sent me an email about that. That's a little correction. So every integer n greater than 0 is divisible by 1, right? So, and it says it's when it's not divisible. So therefore, this is always equal to 0 whenever this is not divisible by 1, because it's always divisible by 1. So therefore, it meets the constraint. So 1 always satisfies this. Okay, can I do that again? This is just logical thinking, although I really should put here n greater than 0, okay? Because it's not clear whether 0 is divisible by 1, okay? So, but every integer is divisible by 1, right? Do you agree with that? So it says here that, so the question is this equal to 0 whenever n is not divisible by 1? Well, when is n not divisible by 1? It's never not divisible by 1. So therefore, in all the cases that don't exist, it's like, it's the empty set. It doesn't ever happen. So it's saying, whenever this thing never happens, is it equal to 0? Well, yeah, it's true because it never happens, okay? Now the other possibility is, let's say d is something else, like 2. So you'd say, well, for any n divisible by 2, is this thing 0, okay? So, whenever it's not divisible by 2. So, in other words, is it 0? So in other words, it says, okay, if it's 2, it means that at time 0, okay, you're in some state, I. And then in time 1, you can't be in state I, ever, probability 0. And time 2, you may be in state I. Time 3, you can't be. So in other words, when you're not in one of the periodic repetitions, if you're out of phase with the periodic repetition, you can't be back in the same state again. You have to exit and stay away until you have a period, and you can only come back to your state at some multiple of that period. If you come back any other time, then you don't have that period, okay? Now, if something is periodic with period n, okay, then if it meets this constraint for period n, it'll meet this period for any prime factor of n. So like, for instance, if n is 10, it'll be true for 5 also. Because so you're saying every period for every interval in between 0 and 10, you have to guarantee you're not, your probability of being in the state is 0. Wait, it's, yes. Right. So every time between, you're sure, okay, maybe it's, okay. It's clear in my head, but that doesn't help you. Where's the eraser? Why are they? This is very strange. Oh, this is, oh God, no, that's not an eraser. What happened to the eraser? Oh, here's the eraser. So let's say the period is 4. This is 1, 2, 3, 0, 1, 2, 3, oh. So n equals 4. So that means that if you pick n equals 4, then the question is, are you sure that you can't be in these states in between, right? So, okay, fine. So let's say n equals 4 satisfies it. So that means that I'm guaranteed that I can't come back to the state. It's like I have to go take a trip. I can't come home for 4 days. 1, 2, 3, 4. I have to stay away for 4 days, okay? I can't come back until 4 days. In 4 days, I may or may not be home, but then I can't come back until day 8, okay? I have to stay away. Now, if that's true, then it also is true for n equals 2, because you're saying, well, I'm saying that I'll stay. That's because if it's 2, I'm saying I have to be away here and I have to be away here, but that's a subset. So the bottom line is, if it's periodic with period 4, it's got to be periodic with period 2, okay? So that's why you have to have this additional thing here, which says it's the largest integer. Because if it meets the constraint with 2 and 4, then you only consider it periodic with period 4. So you take the largest period, okay? You can go look at it more carefully. I think the takeaway here is that you can define a thing called period, and it's a little complicated. It's more complicated than you might think. Okay, but it's fine. Okay, and fine. So now, here's the theorem. The theorem is this. Okay, here are the 3 conditions. Omega is finite. Omega is the set of states. It's a discrete set of states, but it's finite. Why do you have finite? You have finite to keep, okay, these are sufficient but not necessary conditions for the thing to be ergodic. So if you meet these conditions, you're guaranteed that it's ergodic. But they're kind of strong. There are weaker conditions one could have that would still ensure ergodicity. But they're good enough for this class because we can easily show they're true for the problems of interest, okay? So it's not an if and only if condition, okay? Everybody knows the difference between being sufficient and necessary, right? Sufficient means it's good enough, okay? But necessary means, it must be true. Okay, so omega is finite. This ensures that you can't have the states dissipate to infinity. That was the case that occurred when we had a random walk. That the probability distribution just kind of dissipated out to infinity and went to 0. And the stationary distribution was effectively 0. But 0 is not a legitimate distribution because it doesn't sum to 1. Okay. The second thing is the Markup chain is irreducible. Irreducible means that the states all communicate. So it's so that you can get from one state to the next. Okay. And the third thing is that the Markup chain is aperiodic. Aperiodic means that its period is 1. Oh, I didn't give that definition, or it's up there somewhere, but we say it's aperiodic if its period is 1, okay? All right. Does that make sense? And the periodicity, it needs to be aperiodic, because if it's periodic, then it can't reach a stationary distribution, because it's like a clock. It's like a permanent oscillation. So if those 3 things hold, then there exists a unique stationary distribution, okay, of this form. So the pi's are the rows of the p's, okay. And it's the unique solution to these equations, which are the full balance equations. And the full balance equations, that's this. This is in vector form. So that's written out with sums, okay? All right? So the bottom line is this. When you're dealing with Markup chains and you want to figure out what their stationary distribution is, you have to solve the full balance equations, okay? Now, I'll make an observation, which is that the full balance equation looks like an eigenvalue problem where the eigenvalue is 1. Because, I can erase this, I guess. Because it looks like pi times p equals lambda p, where lambda equals 1, right? You remember eigenvalue problems? Okay. So what does this tell you? It tells you that for any matrix at P, which is what they call stochastic matrix, a stochastic matrix means any matrix which has non-negative elements where the rows sum to 1, okay? Because then it's a legitimate matrix associated with the transition probability. They call it a stochastic matrix. It's a misnomer because the matrix isn't stochastic. It's not a random matrix. It's just a matrix that represents a probability distribution, okay, for a transition. Then it must have a unique eigenvalue, eigenvector associated with an eigenvalue of 1. Okay, because it has to have an eigenvalue of 1, because this is 1, that's the full balanced equation, okay? But then the question is, how do you find that eigenvalue, okay? And by the way, all the other eigenvalues have to be bounded, have to have a magnitude which is bounded below 1, right? Because when you keep multiplying by p, those eigenvalues will decay. Okay. So, okay, that's good. Now, right. Okay, so any questions about that? Now, the problem is that okay, so now something really cool is going to happen. Okay, now, okay, so everybody's good with that? So, okay, right. Now, we're going to talk about okay, a reversible Markup chain. Okay, and this always is interesting because I usually get confused when I'm trying to do this. We'll see how it goes this time. Okay. Okay. So reversible Markup chain. So what is a reversible Markup chain? It's a little bit funny in terms of the definitions, but you'll see it makes sense in the end. Okay, so let's say we have a Markup chain. Okay, so we have a homogeneous Markup chain with transition probability P, okay? Okay, and stationary distribution. So let's say homogeneous, and we'll say ergodic, just to make things simple. Pi P equals pi, okay? So then the probability distribution of xn plus 1 equals j, and xn equals I. So that's the joint probability distribution for a pair of states, okay? Remember, the Markup chain is in steady state, and it's a homogeneous ergodic Markup chain, okay? So this thing here is going to be P, it's going to be like P, okay. It's going to be pi I times Pij, right? Do you believe that? Should I write out the reason that that's true? Or is it obvious? Maybe I'll write it out. It's the probability that xn plus 1 equals j, given xn equals I, right? Times the probability that xn equals I, right? Is that correct? You believe that, right? But using our notation, that's just pi I equals Pij, right? Do you believe that? Okay. Now, if it's reversible, that means then, what does that mean? It means that intuitively, it means that if I run the Markov chain forward in time, it should have the same, it should look the same as if we run it backward in time, right? So I'm just to get some intuition going here. We have 0, 1, 2. That's a Markov chain, right? Right? That's a Markov chain. These are the 3 states. And it just goes click, 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 right? Is this periodic or aperiodic? It's periodic. What's the period? 1, 2, 3. 1, 2, 3. 1, 2, 3. It's like a waltz, right? Da, 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 da. Okay, so what's the period? 3, right? Because it's 1, 2, 3, 1, 2, 3, 1, 2, 3. There was an interesting song I was listening to that's an 11, 12 time. No, what was the song? It was really interesting. Oh, I know. Is it the song Money from Pink Floyd? Has anybody ever heard that song before? I think it's in like 11, 12 time or 7, 9 time or some crazy thing like that. Anyway, so this is in 3, 3, 3 time. You know, it's a waltz. So is that reversible? So what does it mean to be reversible? It means that if I reverse it, it looks the same or different? Which is it? Yes or no? Same or different? Same, right? The whole concept of reversibility is that if I reverse it, it looks the, say it for me, guys, just so I'm sure everybody's there. Same, right? It looks the same, right? Does this look the same if I run it backwards in time? No, because it looks like the gears are turning, they reversed, right? So that can't be reversible, correct? That's not reversible. It's not reversible because the probability of getting, the probability that xn plus 1 equals, say, 1, and xn equals, say, 0, that's equal to what? Actually, the answer is it's like 1/3, okay? Assuming, well, it's not really 1/3, but it's whatever it is. Well, it could be 1/3. If I started in a random state, it's 1/3. Okay, but the probability that xn plus 1 equals 0 and xn equals 1, what's the probability of that? So what's the probability of states transitioning from 1 to 0? 0. So they're not equal. That's the point, okay? So if I reverse the order in time, it's not equal, correct? Now, if it's a reversible Markov chain, then these two things need to be what word am I looking for? Starts with the letter E. Equal, right? I just want to make sure, because this isn't that complicated, you just got to keep it straight, okay? So, so the question is, well, the probability that xn plus 1 equals I, given that xn equals j. See, I very slyly reverse the indices here. Okay? So the question is, when is that equal? Okay? Well, this thing I can calculate. This is pi j, and this is pji, right? You got to keep your bookkeeping. You have to do your bookkeeping here very carefully, or you'll get yourself confused, and you can prove almost anything once you get confused. Okay? So the question is, when is pi times Pij equals pi j times Pji. Okay? When are they equal? So this is true if and only if. It's if and only if, but it's really well, it's not quite the definition. Okay, yeah. It's if and only if MC is reversible. And of course, that's for all I and j. So it turns out, more or less the definition of reversibility is that this holds. Okay, because, yeah, the definition of reversible is that the Markup chain has a distribution such that if you take a segment of it and you reverse it in time, its distribution remains the same, okay? But this is the necessary and sufficient condition for it to be true, okay? By the way, a Markup chain has to be stationary to be reversible. It doesn't even make sense. It doesn't have a definite, it's only for the stationary case, okay? So that's why it has to be ergodic and homogeneous in a stationary distribution. Okay, so this is the condition, okay, for reversibility. When the Markup chain has this property, then it turns out that its distribution looks the same going forward and backward in time. Do all random processes look the same going forward and backward in time? No. A lot of very practical random processes look very different. If you take speech, and I think I probably said this to you, but if you reverse speech in time, it doesn't sound like the same, right? Unlike, unless you're playing, what is it, Abbey Road or something, and then it's like, what is it, Ringo's Dead or something like that. Okay, does anybody know about that? Paul is dead, right, or something. You're supposed to play it backwards. It's supposed to sound like Paul's dead. No, okay, but yeah, some crazy thing like that. I'm not even sure it's really true, but that's what the folklore is. But the point is that not all processes, random processes, all physical random processes all physical signals are well modeled as being reversible, but some are, okay? But what's the interpretation of this? The interpretation of it is that if I have two states, okay, and then here are all the rest of the states, okay, and there might be other crazy stuff, whatever, okay, that there's some probability, this is pi I, and this is pi j, okay? So the thing's in steady state. When it's in steady state, there's some probability that you're going to be in state I, and there's some probability you're going to be in state j, right? So that's like, it's as if you were, going to visit and you had a lot of friends, and one night you stayed at one person's house, and the other night you stayed at another person's house. So you'd be like a Markup chain, and asymptotically you'd be spending 30% of your time at state I's house, and 17% of your time at state J's house, right? So that's how the rate at which you visit that state, okay? Now, Pij, that's interesting. Pij is the probability that if you go into state I, you will enter into state j, right? So you might think that Pij is the probability of going from state I to j, but that's false. That is not a true statement, okay? Actually, Professor Buzzer gave a really good example of a fallacy of logic, but the problem is if I say it wrong, it'll really come out messed up. So I got to get it straight in my head first. But this is a classic fallacy of logic people have, particularly if you read the newspaper, okay? Because the problem is that this only tells you the probability of going from I to j, if you're in state I. The actual probability of going from I to j is the product of the probability of being in state I times the probability that you would make that transition if you were there. Okay? So, what was the, oh gosh, I gotta remember. Okay, I'll have to write his thing down. It was really great. Okay, so this is, so pi I times pij, this is the flow rate from I to j. It's the rate of flow from I to j. And pji, this is rate of flow from j to I. So what this is saying is that a Markup chain is reversible if the flow rate between every two states is in balance, right? So here the flow rate is not in balance because if I draw a line between those two states, I go from 0 to 1 more often than I go from 1 to 0. Okay, in fact, I never go from 1 to 0, and I go to 0 to 1 all the time, okay? So, well, not all the time, but a lot, okay? So that's the key thing, okay? Now, here's the thing that's really super clever, okay? By the way, this stuff is like great. It's wonderful fun. I mean, if you can get people to pay you a salary to do stuff like this, I mean, what the heck? You can pretend, all you have to do is make sure you pretend that you're having that it's miserable and it's a lot of work. So they keep paying you, okay? So what happens is that, so you have some crazy network over here, right? And then you have a state. Okay, I'll draw the state in here. And then you have a crazy network over here, and you have the state here. If I can cut the network in two, and if these two states are only connected, okay, through, I mean, if the only connection between the two parts of the, okay, I'm not putting this well. If you have undirected edges between pairs of states, and if I remove this edge, I disconnect the network into two pieces. Okay, in that case, the detailed balance equation must hold. Why? Because you can't just, if you only flow, you just can't, can you see what the problem is? You just can't keep going in that direction. You'd have to come back again. Because if you only went in that direction, eventually you just wouldn't be here. And if that happened, then the probability of flow would be 0 this way and 0 this way, and you'd be in balance anyway. Okay? So the point is that whenever you can cut a network like this by removing a link between two states, if you can, removing a link between two states, you can cut the network, then it means that these two states must obey the detailed balance equation. Because the flow has to balance between the two sides. Any questions about that? Yeah?
So we are always talking about reversibility in the context of periodicity. Like that is an assumed condition for all these things.
Right, yeah. And by the way, my constraints were too strong because I said that all the states have to communicate, and that isn't even necessary here because it can be ergodic without them all communicating because these could be absorptive states, and these could be states that are transient, that you leave and never come back to. Okay? All right, so you got this? So basically, but here's the other thing. So that's the key idea. Okay? But here's the other key idea. If you can, the detailed balance equations are super easy to solve. Reason is you got so many more of them. In the full balance equations, if you have n states, there are only n equations. But here there are n squared equations, so it's way easier to solve them. The problem is that they may not have a solution, okay? They're overdetermined because you have too many equations. So if they do hold, they're really easy to solve. And it's easy to tell whether they hold because you can just look to see what the graph structure is. So here's a classic example of a reversible Markup chain, okay? It's called a birth-death process. So you have state 0, state 1, state 2, state 3, okay? I love this example. It's so much fun, okay? This is how many people have seen this before? Wow, our program really is highly specialized these days. You guys don't get enough, you need to get out sometime, you know what I mean? So this is the Markup chain you use to model getting a hamburger at McDonald's, okay? So the thing is that here you have, what letter do I usually use? Is it rho for growth and mu for death? Yeah, oh, lambda. Okay, so what ends up happening is that this is what's a Q. A Q, right? How do you draw a Q? Oh God, it's been a long time. I think that's how you draw a Q. A Q like this. So when you queue up for a hamburger at McDonald's, okay? The probability of a customer arriving is lambda in any unit of time. And the probability of a service occurring is mu in any unit of time. And presumably they're independent, okay? And so what ends up happening is that you have that pi of I, right? Times lambda is equal to pi of I plus 1 times mu. Because this is a reversible Markup chain, because if I cut it here, it's got to be balanced when it comes in, when it's in steady state. So this is reversible Markup chain. Since this is a reversible Markup chain, it's got to meet the full balance equations. Oh, those detailed balance equations. There's one thing I forgot to say. Okay, so there has to be this. So it turns out that pi I plus 1 is equal to pi I times lambda over mu. And lambda over mu, that's the thing that's called rho. Okay. So what ends up happening is that pi I is equal to pi 0 times rho to the I, or I'll make it n. Then you just renormalize that distribution, and that's the steady state distribution from the Markup chain. The problem is in here, okay? So you can work through the details. The final solution becomes this. It's really cute, by the way. It's pi I is equal to lambda over mu to the I times 1 minus lambda over mu. Now, here's an interesting thing. So what does this tell you? Oh, this is the correct answer when the thing goes to infinity. Okay, when the Q goes to infinity. You can also do the case when the Q is finite. Hi, Greg. I have to ask you what your thing was because I couldn't remember it. But so if it goes to infinity, okay? But here's the other thing that's super interesting that I forgot to mention that is very important, which is the detailed balance equations. So I'm going to write that as DBE. So here's the key idea. Important fact. the detailed balance equations imply the full balance equations. Maybe I'll let you prove that. It's a super trivial proof. You just sum over one of the variables. You sum over I, okay? On this side, if you sum over I, the sum over I of pi is just, if you sum over here, you sum over I. What's the sum over I here? It's just 1, because the rows sum to 1. So this becomes just this, and that becomes the full balance equation. So the detail, if you find a solution, there isn't always a solution to the detailed balance equations. But if there is, then it solves the full balance equations. It's also the equation that it implies that it's reversible. And it goes in both directions. So if the Markup chain is reversible, it has a solution to the detailed balance equations. And if the detailed balance equations are solved, then the full balance equations are solved, and it's ergodic, okay? So, and usually it has a graph structure that looks like this. Why, you may ask, do we worry about this, other than us being able to analyze the queue at McDonald's? Oh, by the way, if the arrival rate's greater than the service rate, what happens to the queue? It blows up, right? Which is what happens at lunch. So the thing here is this. We're going to use this. Because when we do stochastic simulation, Monte Carlo methods, those methods are almost always reversible Markov chains. Because it's the only way you can prove that they're ergodic, okay? It's sort of the practical bottom line in terms of how you do it, okay? All right, thanks a lot, bye.